Our next speaker is Alison Gopnik. Professor Alison Gopnik is a professor of psychology and also affiliate professor of philosophy at UC Berkeley. And she has been doing a lot of pioneering work in developmental psychology and social psychology, and has won numerous awards, right? She's the fellow, or actually elected member of Society of Experimental Psychologists and AAAS, and also a fellow of Cognitive Science Society and another AAAS. And not only being a popular, well-known scientist, but she's also a very popular writer, has co-authored a number of books that are best-selling and widely acclaimed. And her TED Talks has also been very popular and watched over 4 million times. And I think in recent, my understanding through my conversation with my advisor, Josh Tenenbaum, is Professor Gopnik has been very interested in building computational models for developmental psychology for a long time, but especially recently, as we all know, like that's the reason that we have this workshop, is in the past few years, there has been a lot of interest, not only from, especially also from the AI field, that how can really bring common sense and bring the way that children's or infants learn into machine learning. And so, and these days, Professor Gopnik has also been collaborating with people in computer science department of UC Berkeley on developing these computational models, bringing knowledge from psychology and cognitive science. So today, Professor Gopnik is going to present Children's and Masses, Model Building Exploratory Social Learning Systems. So welcome. Thank you, Alison.
Well, thank you again very much for inviting me. And I'm very glad to be part of this workshop, which is talking about ideas that I've been thinking about for a long time. And one of the things that, of course, is exciting about the workshop is this idea of combining the things that people in developmental psychology and child development have looked at for many years and problems that people in AI are thinking about. Now, it turns out this is not actually a new idea. Many of you have probably seen this, this quote. Alan Turing in 1950 already thought that instead of trying to produce a program that simulates the adult mind, we might do better by producing one that actually simulates the child's mind. And the reason why Turing thought this was because children have this incredibly great learning capacities. And during the long period when AI was mostly focused on trying to program in knowledge into a computer, I think the importance and significance of learning was kind of backgrounded. And of course, as we've heard in the last 10 or 15 years, a lot of the big advances in AI have come because of advances in our understanding of learning. So if you think that the route to develop common sense is through some kind of learning, then children are obviously the right people to look at. They're the best learners we know of, and they definitely are learning a lot about the common sense world by the time they're toddlers. But if you actually look, and again, this will echo things that other people have been saying, if you actually look at the kind of learning that has been so key to the advances in AI, things like deep learning, supervised learning, deep reinforcement learning, it looks very different from the kind of learning that we typically see in children and the kind of learning that seems to be responsible for their amazing understanding of the world in this kind of common sense way. In particular, AI learning needs lots of data, and it's typically worked on these very large data sets, and very large data sets that are notably curated by human beings. And it doesn't often generalize in the right way, or even generalize very much at all. And things like adversarial examples are good examples of the fact that AI systems will generalize in ways that just look wrong from the perspective of common sense. On the other hand, the great advantage of these systems has been that they work. So we can actually use them to solve problems, at least at a first pass, like object recognition or speech recognition. Now, if you compare that to 4-year-olds, 4-year-olds are sort of almost the opposite of this. As you've seen from Linda Smith's beautiful work, the kind of data that they're seeing is very different from the kind of data that you typically have in, say, in a large a data set like an ImageNet data set. So they're getting lots and lots of information, but about relatively few things in a relatively constrained setting. There's very little supervision or reinforcement. Most of the time, the children are just soaking up things that are going on around them. On the other hand, they do excellent generalization. And from the kind of work that Liz Belke or Josh Tenenbaum has talked about, you can see how good children are at generalizing to very different new situations. And that's going to be sort of a focus of the work that I'm going to talk about today. On the other hand, we don't have very good computational models of how this is possible. And in fact, the best models that I think we have, which I'll talk about in a minute, things like doing Bayesian inference about probabilistic generative models, are computationally intractable. They come up against exponential kinds of search problems very quickly. So the question is there some way of taking these things that 4-year-olds do, using it to make an AI system that would be more effective? And this whole symposium is part of this bigger project that DARPA has sponsored, this Machine Common Sense project, designed exactly to try and figure out if we can build a machine that has the common sense of a toddler. And our contribution to it from Berkeley, we rapidly learned that the most important thing about DARPA was thinking of good acronyms. So our acronym appropriately for children is MESS. We think there are 3 elements in the way that children learn, different from the typical ways that, at least until recently, AI systems have been learning, that enable them to learn so much about common sense. One of them is that they build models, in particular abstract causal models from statistical evidence. Another thing is that they learn through imitation and social observation. And then the third thing is that rather than being stuck in their mainframes, they actually are active learners. They go out into the world and actively get information about the world. Now, in my other CVPR talk in the Embodied AI workshop, I was going to say yesterday, that's actually happened in parallel to this workshop. I talked a lot about new work that we've done on this last point about active learning through exploratory play. Beautiful work that Alison Gopnik, my graduate student, and some of the people at Berkeley have done. So I'm only going to talk about one experiment that looks at that today, mainly because it's just such a neat experiment I can't resist. And it speaks to some other things as well. But mostly what I'm going to focus on is that this first point, which is this point about inferring abstract models, particularly abstract causal models, from statistical evidence in the world. And that seems to be at least one of the things, as we'll see, that children are extremely good at doing. And if we could design computational systems that could do the same thing, then they would be much more powerful than the kind of systems that we have now. So what do I mean when I'm talking about these kind of abstract causal models? What we're talking about are abstract structured representations. They could be of many kinds of knowledge. The work that I've done is particularly about causal knowledge that have systematic relationships to data. And in fact, the first way that we started thinking about these things way back in the 90s, even in the 80s, was to think about them as being like intuitive theories. And Josh talked about a kind of intuitive theory of physics, intuitive theories of psychology or intention or utility and so forth. And intuitive theories are abstract generative representations, structured representations. But not only are they abstract representations, but they're systematically related to patterns of data. So if you have a theory, theories are built out of evidence. And if you have a theory, you can make predictions, novel predictions about patterns of evidence. Then in the 90s and the early aughts, this idea of an intuitive theory got formalized, particularly with the whole causal Bayesnet, causal graphical model representational system. Probably the person who people in AI would know best in this regard is Judea Pearl and Judea Pearl's work. But there was also very interesting work in philosophy of science, very similar formal work at about the same time, what's sometimes called formal epistemology. In particular, the philosopher of science, Jim Woodward, who I'm going to talk about in a little bit, has a beautiful book actually specifying something about how you could formally describe these kinds of causal systems. And Clark Lemore, who is my longtime collaborator, philosopher of science, also did work in the same, along the same lines. And then more recently, there's been a lot of work, again, Josh talked about this, going beyond just thinking about these causal graphical models, developing more abstract kinds of models, and particularly developing something like a kind of probabilistic logic or a probabilistic language of thought, taking these basic ideas and generalizing them beyond just causal relationships among variables. Now, the advantage of having these kinds of generative probabilistic models are twofold. First of all, if you have this kind of abstract generative model, then you can go from causal structure, for example, to make statistical patterns, not just patterns about predictions, but also patterns about predictions about counterfactuals or about what will happen when you intervene on the world, which is important from the perspective of thinking about active learning and exploration. But one of the consequences of the, and a lot of the work that's been done, again, I think Josh and Liz's work on core knowledge is a good example of this, points out that once you have these kinds of probabilistic models, they will really help you to learn about the world because they'll constrain the set of possibilities that you'll consider in important ways. They'll tell you something about the kinds of inferences that you should make given certain kinds of patterns of evidence in the world. And again, things like the intuitive physics or intuitive understanding of space are really nice examples of that. But from my perspective, these models also do something further, in some ways, at least from my perspective, even more interesting, which is that they also give you computational accounts of causal learning. So they give you a way of talking about how you could reverse that inference, go from going out in the world and seeing statistical patterns and actually inferring new kinds of causal structure you didn't start out with, causal structure that might be totally different from anything that, for example, is in the environment in which you evolved. And one of the things that's really striking about human beings is that we're very good at learning about things that we really couldn't have anticipated in the first place, learning about new kinds of systems, learning new things about the causal systems around us that we could never have thought of beforehand. And I think what we've started to show is that this is even true for toddlers. So even toddlers, as you'll see, can take very small amounts of data and make surprisingly powerful inferences about the structure of knowledge in general and causal structure in particular. And what I'm going to do, so over the past, now I hate to think this, 20 years, I and others and my collaborators have had lots of examples showing how good children are at doing this kind of learning, at learning new probabilistic causal models from patterns of data and evidence, inferring complex causal structure. And these are two papers from 2012 where I reviewed this sort of decades worth of research showing this. But even though you have a system that can do all of these things, there still are some really serious, deep problems in trying to learn a generative model like this from data. And I'm going to talk about two of those problems today, and if not provide solutions, at least show that toddlers can solve these problems, that toddlers actually can learn causal models from data in this way. One set of problems that we've looked at in the past is whether, in addition to inferring specific causal structure, like what variable is responsible for what outcome, can children infer abstract causal structure? So can they infer things like whether a generative model follows a certain logic or not? Is it conjunctive or is it disjunctive, for example? And in a bunch of work after the reviews that I just mentioned to you, Tom Griffiths and Chris Lucas and I showed that, in fact, very young children, 4-year-olds, can do this. And not only can they do this, but they're actually systematically better at inferring these abstract aspects of structure than adults are. And the reason why they're better is because they have less peaked priors. They seem to have flatter priors, fewer assumptions about how the world actually works, what the abstract structures in the world are. And the fact that they have those fewer assumptions actually makes them better learners. And I'm going to give an example in a minute of some other instances where children are actually going to be better learners than adults are. And just incidentally, one of the things that we are increasingly recognizing in development is that we tend to think about our common sense just based on our particular, weird experience of the world, the common sense of academics in California. But in fact, we've done things like gone out to low-income areas in the outskirts of Lima in Peru, and we've shown that these children, or children in Head Start programs in Oakland, are just as good at inferring this abstract causal structure. In fact, in some ways better than the children in Berkeley are. And like the children in Berkeley, they do a better job of making these inferences than adults do. Okay, so the two problems that I'm going to talk about today, The first problem is a problem that, again, the philosopher Jim Woodward calls the problem of variable choice. So even if it's true that given, say, an abstract causal structure with different kinds of variables and relations among them, you can learn something about how those variables are related to one another, in the real world, a big problem in making any kind of inference about a generative model is trying to decide what kinds of variables you should even pay attention to in the first place. So if you're looking at an actual real scene, as we know, it's not at all trivial to try and figure out which aspects of the scene are the ones that you should even be computing on in the first place. And very often what we do is sort of pre-specify, here are the kinds of variables that we're interested in, here's the kinds of objects that we're going to be interested in, and then we start trying to figure out the relationships between these objects. And Jim Woodward, the philosopher, has talked about this as the problem of variable choice. So what we wanted to see was, could young children actually solve this problem of variable choice? Could they figure out which are the things that are relevant and which are the things that are irrelevant, particularly in a causal setting? And the central idea, so here's the problem, how is it that we can actually construct a new variable based on old variables? And the central idea that, that Jim talks about, this is consistent with a lot of work in the philosophy of causation, is that causal variables are difference makers. So what you're looking for is things that are going to actually make a difference in what happens out in the world. And the question is, can children use this pretty abstract idea of difference making to identify relevant causal variables in the world? That may sound like something that is kind of impossible to ask 4-year-olds. How could you ask 4-year-olds whether they think causal variables are difference makers? That's why we developmental psychologists get the not very big bucks. So here's how Mario, my brilliant graduate student who's responsible for all the work I'm going to talk about here, how she figured out how to do this. This is the turtle game. This is Shelley the turtle, and he likes to eat cactuses. But he likes different cactuses at different times. So he likes to eat cactuses with square fruits on them for dinner, but for dessert, he likes to eat star cactus fruits. And what we want to do is help poor Shelley to get the kind of cactuses that he wants. Well, how are we going to do that? Well, here's how the cactus games go. We're going to grow the kinds of cactus fruits that Shelley likes to eat. And we have cactus seeds and pots and watering cans. We have all sorts of different pots with different stripes, and we have all sorts of different watering cans of different colors. And we want to try some of the pots and some of the watering cans to grow the right cactus fruits. So here we go. First, we try this striped pot. We put the yellow watering can on. Oh no, there's round fruits. Look at poor Shelley, so disappointed. Well, let's try something else. This time what we'll do is we'll try the other pattern. And we'll try the other pattern with that same watering can and see what happens. Oh no, we've got round fruits instead. Now, how about if we do this though? How about if now what we do is we keep the pot the same and we change the watering can. Now we have a blue watering can. Look what happens. We get square cactus fruits for Shelley. And Shelley's really happy. So now here's the crucial question. Now it's dessert, right? Remember that Shelley likes the stars for dessert. And so we take a new watering can, a new pot, and instead we get triangles. We don't get the stars. Now, the crucial question is, which one should we change if we want to grow the star fruit? Should we change the pot or should we change the watering can? In other words, to put it in philosophy of science talk, which is the causal variable that is the causal variable that's the difference maker? So is it the pot that makes the difference, or is it the watering can? And if you think that difference making is what tells you the relevant causal variable to intervene on, then you should choose, in this case, the watering can. Obviously, we counterbalance. And in fact, that's just what 4- and 5-year-olds do. So these 4- and 5-year-olds already can use this quite abstract statistical feature of the world, what's the difference maker, to decide which variable is actually the relevant variable and which variable they should therefore intervene on. I think I will skip over the next one in the interest of time, but just point out that we got a more concrete version of this. And in this more concrete version, even 3-year-olds are solving this problem. So now when the 3-year-old has to decide, do you change the bell to make the machine go, or do you change the switch to make the machine go? The children are choosing the appropriate relevant variable. And interestingly, they're even choosing a new value of that variable. So they think you should choose a new bell, even if they've never seen it before, to try to bring about a new result. So this is an example of children solving this very difficult variable choice problem by using quite an abstract bit of statistics to solve it. Now here's another kind of problem. This is a problem that I think is very related to the compositionality issues that have come up several times. And this is a problem about learning and using causal functions, not in the sense of something being functional, but in the mathematical sense. So one of the things that allows you to have compositionality is to have representations that include functions. So if you know, for example, that something has one value on one dimension, but that it's got a particular kind of, subject to a particular kind of function, then you can make a really wide range of general and new predictions about the value of another variable. So if you have two variables, you know that they are related by a particular function, then you can make brand new predictions about what the value of one variable will be given the value of another. Let me give you a concrete example of this. Here's Alice, who's her regular size, and she decides to drink the liquids that's in the drink me. And what happens? She gets little. She gets to be littler than a mushroom. And then she nibbles on the side of the mushroom and she gets big. She gets so big that she ends up being in a house. Now, that kind of set of functions, things get bigger, things get smaller. You take a drink or a nibble on a mushroom when you're in Wonderland, and either you get very, very littler than a mushroom, or you get so big that you're bigger than a house. Being able to make that prediction that if you get far out on the big function, you're going to end up being bigger than a house. Whereas if you get far out on the littler function, you're going to be littler than a mushroom. That's not something that you can ever infer from, say, the data that you'd see in ImageNet, because you're not actually going to see examples of things shrinking to the size of a mushroom or a person becoming the size of a house in real life or in real data. And yet, nevertheless, every child who loves Alice in Wonderland immediately gets it about what these relationships are like. And I think this is important because, again, this relationship of shrinking or growing isn't something that you would see out in the real world very often. But once you understand it as this abstract causal function, then you can end up making these really striking counterfactual predictions, very different from anything that you could ever just extract from looking at the data. So the question is, could even young children, could even toddlers learn and use these kinds of functional relationships? And again, this is work with Marielle. And what Marielle did was to invent these change machines. And here's how the change machines work. What happens is that we introduce the children to a music box that has a hole and a shape that has to fit on an outline in order for the machine to play music. So it could be too big, it could be too small. And then we introduce the children, these are 24-month-olds, really toddlers, to two change machines. And one of the machines makes objects bigger, and one of the machines makes objects smaller. So let me show you how this works. You see that there's a music box, and some shapes make the toy play music. In particular, it has to be the right size. If it's too small, it won't make the machine play music. If it's too big, it won't make the machine play music. But if it's just right, again, children's Goldilocks story, then it will make the machine play music. And then we introduce, so that's the music box training. Then we introduce the child to these two change machines with blue and yellow doors. I hope you can see this in the picture. So we put a tiny, tiny little yellow animal into the change machine, into the yellow door. And what comes out is a much bigger version of that tiny little orange animal. And then we show the children the same thing, except, in half of the cases, we show the children the same thing, except what happens is that the little animal gets to be much smaller when it goes into the blue door. We show the children in both cases that the animal gets much smaller when it goes into the blue door. And then at test, the children have to choose which machine they want to put this object in. So for example, you get an object that's much too big to fit the shape on the music box. And the question is, should you put it in the expanding machine or should you put it in the shrinking machine. I hope everybody's kind of got the logic behind this. And it's important to notice that the actual sizes of the objects at test are very different from the size of the objects that have gone into the machine. So you can't solve this problem just by saying, I want something that's the same size as that machine produced. The only way you can solve it is by understanding the function, I want something to get bigger or I want something to get smaller, even though the new objects at test are totally different from the objects that the children have seen before. So now the question is, let's see if this shape plays music, and which door should we put it in to get it to play music? And what we found is that this is all pre-registered and then replicated, is that even these very young toddlers, even in a brand new context, even with only 2 pieces of evidence about how those machines work, can extrapolate from the information that they already had. And not only can they extrapolate from it, but they can use it to solve a new task which they haven't ever seen before. Let me give you one last example now, talking about exploration, about the kinds of techniques that children can use for figuring out the causal structure of the world. So in the examples I've been giving so far, children have to figure out the structure, but there isn't really anything riding on the structure aside from just figuring it out. In these experiments, we wanted to see what would happen if there was actually a tension between the drive to figure out the structure of the world and the kinds of reward that you could get. So what we did was we took a kind of amalgam of our causal learning tasks and a classic reinforcement learning task. This is work with Emily Liquin. So what we did was show children a box that has blocks that you can put on, and you can either approach or avoid the machine. If you put the block on and the block is a ZAF, we tell everybody that ZAFs make the machine go. And if it's a ZAF, you're going to get a sticker. On the other hand, here's another block, a black stripe block, and you put the block on now and you actually lose 2 stickers. I gave this talk in Silicon Valley recently, by the way, and I figured I had to change it to like 2 billion stickers that you either lose or gain to actually make it be relevant for that audience. Now you see a yellow block with white dots on it, and sure enough, you get a sticker. Now here's the question. You're the one who's regulating this. You're doing active learning. What should you do now when you see this yellow block that has black dots on it? Should you approach it or should you avoid it? Now, if you're trying to exploit, if you're trying to just maximize the reward that you'll get the way that, say, something like deep reinforcement learning would do, then the sensible thing to do is to avoid it, because A, you're going to lose more than you're going to gain, and B, there seems to be a very simple hypothesis about which blocks are responsible for making the machine go, which are ZAFs and which aren't, which is that black ones are not ZAFs and white ones are, so you should not put this on the machine. But there's obviously a downside to this, again, part of this classic exploration versus exploitation trade-off, which is, how about if it actually is a different principle? How about if this is a ZAF? And the principle for ZAFs and not ZAFs is this 2-dimensional hypothesis, this initially unlikely hypothesis, which is that black striped ones are not ZAFs, but everything else is a ZAF. Now, what will happen is you'll never learn that rule if you always are avoiding the ones that you think are not ZAFs. And in fact, Todd Gorekas discovered that that's true with adults. So adults get stuck in what people sometimes call a learning trap, where they'll avoid ones that they think are going to lead to a negative reward. Again, what a classic, reinforcement learning algorithm would do. And the result is that they never actually learn the rule. And you can see that adults are only getting about half of the examples of positive of ZAFs. They're only identifying the ZAFs correctly about half of the time. But when we look at 6 to 7-year-olds, they're actually doing better. And 4 and 5-year-olds are doing even better. So 4 and 5-year-olds are certainly approaching much more. So they're more willing to risk the negative outcome, losing the stickers, in order to get the information. Now, how about if we ask about learning the causal structure, learning the structure of this system? What we discover is that the adults are actually doing a bad job at learning. Remember, the 2-dimensional rule is actually the right rule, particularly as in our previous experiments, doing a bad job of learning these unlikely outcomes, this unlikely rule. And the 4 and 5-year-olds are are doing much better. So the 4 and 5-year-olds are actually learning the role better than the 6 to 7-year-olds, who are doing better than learning than the adults. So part of the idea is that if you have a motivational system that's based on things like curiosity and exploration, rather than based on simply reward, which seems to be true for children in childhood, you might actually end up doing better at inferring causal structure, inferring generative structure, particularly inferring unlikely or novel kinds of structure in the environment, than if you are just doing something like using a reinforcement learning algorithm to maximize reward. So let me backtrack a little bit. We don't know exactly how to implement these procedures computationally, but I think it's important to say that they're all things that could be represented in an abstract computational way. They're all things that, to get back to the point about which questions you want to ask, they may be inspirational now, but I think they're kind of close to being actionable. They're things that you could imagine designing systems to do. So for example, using difference making, using difference-making patterns to try to decide what kind of variables you should be paying attention to and which ones you shouldn't. Learning and using these abstract functional relationships between variables to solve really novel problems, to make really wide-ranging kinds of generalizations. And prioritizing causal learning and exploration over reward. We've been collaborating with Deepak Pathak and Pulkit Agrawal and others at Berkeley, trying to use these kind of curiosity-based RL systems to try to mimic the kinds of things that we see children doing when they're trying to explore. So let me end by saying, so I think Turing was clearly right that we should be looking at children to get inspiration for programs, but it may not just be that children are a kind of sufficient condition, that we should look at toddlers. I think a little bit of the rationale behind saying things like, could we get a machine that could be as good a learner as a toddler is sort of, okay, well, toddlers, like, they're not really that smart. Like, it might be really hard to get a machine that could learn as well as a grown-up could, but at least we could get them to be like a toddler or a jumping spider or a crow or whatever. And in fact, I think the data kind of suggests the opposite. They suggest that it might be that if you could get a system that would be as good as children, you would really have the right thing. You'd really have a system that's intelligent and designed specifically for learning. And in fact, what I've argued most recently in this paper, which has just come out in the Philosophical Transactions of the Royal Society, is that you could think of children in childhood, this long, protected, very distinctively human period, one which we don't share with other primates and which looks as if it's extremely costly. If any of you are sitting at home with your 2-year-olds as you're attending this conference, you will know what I mean. What kind of function could that serve? And what I've argued is that childhood might, in fact, be evolution's way of doing something like simulated annealing, having an early period of wide-ranging, high-temperature, variable kinds of search that allows you to explore the space widely before you narrow in on, say, exploitation and reward. So it might not be just that it would be good if you had systems that were as good as toddlers, but toddlers might be exactly the right people to help you design a genuinely intelligent artificial system. And let me mention my collaborators in support, my computational collaborators for a long period, Clark Lemore and Tom Griffiths and Chris Lucas, and especially Marielle Gadou and Emily Liquin, who of course did all the work, and the supporters of the research, especially the DARPA Machine Common Sense program. And let me take some questions.
Yeah, thank you, Alison. A very great talk. So let's see, are there any questions? There's one, okay, there were 2 raising hands. The first is from Calvin. Oh, I think Calvin put down the hand. So I guess the other is from Aaron Sloman. I think the other, oh, that's fine. There are 2 questions, one from Aaron Sloman and one from Ajay Diva. Sorry, I think the name was occluded. So
I think I've unmuted Aaron.
Can you hear me?
Yes.
Yeah.
I like that very much. And I think it's closely related to some ideas that Jackie Chappell, who's a biologist, and I have been developing over the last 15 years or so, which we now call the meta-configured genome. It includes, I mean, I can't go through all the details, I can send you links, but it includes the notion that at various stages, the genome has mechanisms for generating motives which have nothing to do with current rewards or expected rewards. They're just opportunities that are detected that generate actions, and information is picked up of that through that kind of thing and accumulated. And then at a later stage, another part of the genome becomes expressed, which looks around in records to find out what has been picked up from these earlier interactions, and then can instantiate general patterns in a way that is modified by the results of those earlier explorations. So you get the same genome producing very different patterns of development in different cultures, epochs, and so on. And I think it's very closely related to what you were saying, but that might require some more detailed discussion. And I suspect that there are other animals that have similar capabilities, other intelligent animals like squirrels and various kinds of nest building birds and so on. But humans have more layers, and everything is more complicated in the case of humans.
Well, I want to recommend, yeah, I think that's right. And I want to recommend that the special issue that just came out, my paper is just one, I actually co-edited it. And it's a lot of the papers in there are actually from evolutionary biologists. The general theme is this theme about life history and learning. So the idea is that we tend to think, including in thinking in AI, in terms of, here's the, adult human who happens to be the person who's designing the AI system, who's kind of the peak of potential intelligence. And if you actually look at it from a biological perspective, you see really different kinds of intelligences at different developmental stages in a creature. And I think this is connected to some of the things that that Linda was talking about curriculum learning, where you see very different kinds of computational capacities in, and again, this is not just true in humans, this is true in crows, it's true in other primates, between, say, juveniles and then animals that are mature, and also, interestingly for humans, later on in old age. So it seems as if what happens is that we've got a bunch of very different systems, all instantiated in one individual. You could think of it as being sort of multi-agent learning in the course of a single human being in the course of a single lifespan. So we have these kind of trade-offs between very early, very good at exploring, not very good at exploiting, then a kind of midlife, very good at exploiting, no longer so good at exploring, and then quite plausibly an older niche that's about some things like cultural transmission or teaching or pedagogy. And I think it's a very interesting idea about this kind of contrast. And you see this even in, it's very, very general in evolutionary biology. You see these contrasts even in insects, for example. Go back to Bruno's jumping spiders. I don't know what the baby spiders look like versus the older spiders, but you can see some of these contrasts even there.